Hello, everyone. Welcome to a talk I'm going to be giving on bipartitioning based legalization and analytical placement. So bipartitioning is a very fun algorithm. It's a great divide and conquer technique. It's great at removing overlap. And it's something that we might want to investigate if we want to use it for things like analytical placement. So I wanted to talk about some of the papers that use this technique. So first of all, a reminder on how analytical placement works. This is going to build off of the previous discussion reading group I had about a month ago. So we have the very first step of analytical placement is we're going to solve some sets of equations. These equations are idealized where we've relaxed a lot of our constraints in order to be able to solve some objective like wire length, timing in an analytical way. So we solve those equations, and what happens is because we've ignored constraints, like for example, this yellow block cannot exist in a block that has these blue blocks. So it has to be in here. So we've relaxed that constraint to allow it to be a little bit more illegal to hopefully find a better solution. Same thing with these purple blocks. And if you can see here, these blue blocks, thanks, Hyder, these blue blocks are all on top of each other. This one tile right here can only hold, let's say, 4 of those little blue balls. That's way too much overlap. So what we need to do is find ways of spreading out this overlap by spreading these blocks away from the regions they're not supposed to be and trying to inject the constraints. And by slowly injecting the constraints while continuously solving our equations, we begin to approach a legal solution. Now, it's not fully legal. For example, we say these 4 atoms can fit inside this block, but some of our friends here are working in clustering, and they probably know that you put some blocks in somewhere, it doesn't necessarily mean they'll form a cluster. So this isn't fully legal, but we got really, really close. And it gives us a global shape of what this placement is going to look like. So we're saying, I don't know if this is 100% legal, but I'm pretty sure these atoms want to be near each other towards this bottom region of the chip. These atoms want to be up here. And you can see, even though these guys are strongly connected, or connected in some ways, they've been spread out farther apart because they have stronger connections elsewhere. And then finally, once you've gotten your global placement, you pass this into a full legalizer that actually builds the real clusters and actually places them truly on the chip. So this is an overview of how analytical placement works. Any questions on this so far? So the intention for today's presentation is how do we spread these blocks? We want to remove these overlaps. We want to make sure blocks are existing in tiles that they can exist in. How are we going to do that? So the legalization in analytical placement depends on the type of placer. So when I want to try and legalize, spread these things apart, for nonlinear global placers, this is just a reminder from last month's presentation, the legalization is baked into the objective function in forms of penalty terms. If you recall from last week's discussion, we talked about E-place, which used an electrostatic formulation, which said that atoms that are too close together to each other, they're going to feel a force that repels them, or a penalty to the cost function, saying, although we want to reduce the wire length here, they're so close together that that term starts to add up, so it repels them. So that's how nonlinear global placers tend to bake in legalization. Quadratic global placers tend to be put into the following camps, where it's limited in what penalties it can be applied to the objective, since it must be quadratic. I can't just apply penalty terms using differentiable functions. I need to be careful with how I apply the penalties to the objective. One option is we can apply forces to the blocks directly. You can imagine this like I have those blocks and I see they're close together and I apply a force to them that pushes them away. This is similar to the approach used in FastPlace. And you can also apply forces from blocks to other blocks. So for example, if I know that the position of this block should be over on this corner of the chip, I may make a fake block and add a connection between them, pulling them towards that position. And mathematically, these become basically the same thing, but it's 2 different ways of thinking about how I can modify my quadratic global placers. We'll also talk about a couple other quadratic global placers, which actually modify how the quadratic function is solved in general. We'll see 2 examples of this. One of them is actually turning it into a constrained quadratic function, and the other one's actually changing how the connectivity matrix is constructed. But the goal is still the same. We need to resolve this density quickly. If the legalization that you perform inside of your global placer is quadratic, for example, that is not acceptable. That means I look at a block and say, okay, look at all the blocks nearby. Well, if all the blocks nearby happen to be all the blocks in your net list, and you do that for every single block, that's going to be number of blocks squared. And ideally, what we're looking for is we need something with a low time complexity. So something like n log n at worst. So that's why we're probably going to want to look into something like bipartitioning. Bipartitioning for legalization says the following. Let's look at this space of, and we see dense regions, we see not so dense regions. And what I'm first going to do is partition the space. I'm going to partition the space in half. Then I'm going to move the blocks onto the side that they're closer to. And then I'm going to repeat. So what I'm going to do is I'm going to partition the space. I didn't make the animations to move the blocks because I'm a bit lazy, but imagine the blocks move to their different partitions. You create another partition line, move the blocks so that, and the goal here, the reason why I'm doing this is that the amount of space on the left is about equal to the amount of space on the right. And I move the atoms to the side so they have enough space to sufficiently hold them. And I move all the atoms to the right so they can sufficiently hold them.
This is an important one to throw that into. So you bipartition the space.
Yep.
But now you do not, you're gonna basically scan through all the blocks horizontally.
Correct.
And you're gonna determine the point at which you have half the mass on the left and half the mass on the right.
Right.
Which will not be where your cut line is. It's some other spot, probably to the left of it here.
Yes.
And everybody to the left of that line will basically be in the left region. Everybody to the right of that line will be in the right region. So some blocks are moved in terms of which region they belong.
Correct.
Okay.
If you had homogeneous blocks, like all these blocks were the same exact thing, you could literally sort them by their positions and then pick a middle point. But in this case, we don't have homogeneous blocks. I see these little, and the colors don't come out very well. There's a purple block right here. That one has to be on the right partition. And these yellow blocks have to be on the left partition. How you handle that is something that my paper looks into, but we're not going to talk about that this week. So yep, we partition, and I'm only going to show the left partitions. We just keep partitioning, 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 partitioning until we reach a point that we cannot partition much farther. So the idea here is, let's imagine we had a perfectly filled chip. We've overfilled this chip to the point that every single tile is going to be filled. This is going to put half the blocks on one side, half the blocks on the other. This one will put a quarter down here, a quarter up here. This one will put an eighth and eighth, a 16th, 16th, and so on. And the idea is eventually we'll get down to the point where this region right here, after we moved all the blocks, will have the exact amount, will reduce the density enough so that it is not overfilled anymore. So that is the intention of bipartitioning. And one of the main benefits of this is a divide and conquer algorithm. Once I put everything on the left, once I'm looking at this partition line, this one right here, I don't need to consider any blocks that were placed in the right partition. I've cut my problem in half. And then I cut my problem in half again and again and again. This comes out to being an n log n style algorithm, which is why it's quite desirable to use. So the pros and cons of this approach: pros, divide and conquer, very easy to parallelize. I can do one partition while I'm working on the other one. For example, it's very fast, n log n, where n is the number of blocks being spread. And it directly resolves the density. It isn't like trying to negotiate with blocks saying, okay, you moved over here, now I'm going to move over there. It directly says, you go to the left, you go on the right. Next partition. You go up, you go down. Next partition. And it doesn't rely on any kind of convergence criterion where things move towards us closer and closer to a legal solution, for example. The cons of this approach: it has no concept of the objective. It's really just saying move things as close to where it can be without regard to, okay, well, if I move this block all the way over here, this one has like 6 edges connected to it. That might be very expensive to move. Now, you can inject things into the objective into this, but that adds more complexity and can add more runtime. And so blocks can't negotiate for which partition to go in beyond their present location. And they make decisions very early. The problem is that when I make my first partition and say, you guys all go on the left and you guys all go on the right, as I keep legalizing, I might realize that, maybe that was a really bad idea. I have a block that was on the left that really preferred to have been on the right, but I didn't know that at the very first partition line. And once I get to the end, I can't repartition without breaking all the stuff I've already done. So that's something we're going to see how other papers have gotten around. Papers have to get around this decision, get around this problem. So unless dealt with, this can actually have a really bad effect on quality because you're putting things on the wrong side very early on. And for legalization, this is often performed in quadratic global placers. You don't really see bipartitioning being used in the nonlinear ones, or at least I haven't seen many examples. The examples I'm presenting today are all quadratic placers. Any comments on this? Awesome. So we're going to get into what places we're going to be talking about. Now, I'm only going to be talking about the ones on the left because I foresee I'm not going to have a lot of time. So I'm just going to be talking about analytic placers that use bipartitioning for legalization within the objective. What I mean by that is they've taken their quadratic formulation and injected bipartitioning into the formulation itself. This is different than how it's done in like simple, for example, which does a global placement followed by a legalization. Then they feed the information back in and solve global placement again. Then they do legalization again. What these do is they actually change how the objective function is written in order to make it so that it injects the partitions. I'll show two examples of that, which is going to be Gordian from 1991, which is an ASIC placer, and BonnPlace, which is from 2007, which is also an ASIC placer. And then next week, we'll talk about the separation approach, these are all based on simple. So simple from 2012, which is an ASIC placer. Then heap, which is from 2012, which is an FPGA placer based on simple. And then gplace 3.0, which is from 2018, which is also an FPGA one. So I'm going to get into Gordian, but people ready for this? All right. So Gordian. I like this paper a lot because the name is amazing. So are people familiar with the Gordian knot? Yeah, I know Vaughn is. The Gordian knot, it was Alexander the Great, actually. So basically, yes, exactly. The idea is that there was a giant knot that no one could untie, and they say, whoever can untie this can become the king of our lands. Alexander the Great came in, looked at the knot, and cut it in half. So this was a very good analogy for what this one does. We have a very knotted circuit that we do global placement on, and we have all these knots, kind of like that very first picture that I showed at the beginning. We have a circuit with a bunch of knots in it, and we need Alexander the Great to come in and cut this knot in half.
Why do you like the title of that paper? You are going to work this into the title of your analytic placer somehow.
I just think it's very clever. But anyways, how it works is the following. They have a global optimizer, which is minimizing wire length. So we have a minimized wire length objective. This global placement is performed, and the module, they call them modules, you can call them blocks, whatever, the things that are moving, they pass those coordinates into the partitioner, which will partition the space, and then pass the partitions back into the global optimizer. The global optimizer will then use these partitions to say, okay, find me a global placement, but this atom must be on this side, and this atom must be on that side. No interchange. And so it solves global placement, and then it goes back and does partitioning again, then it passes it back, and so on, successively cutting the space, global placement, cutting the space, global placement, cutting the space, global placement. And a little bit of extra magic going in there. And so overlap removal, which means like the legalization is occurring by the partitioner. And as you can see, the position constraints are passed into the global optimizer. This is what I mean by the partitioning is happening in the objective function. We're not actually performing like an external partitioning, and then we're doing a full partitioning. We're basically modifying our global objective. And I'll show you what the equation looks like for this. Everybody good so far? So Gordian represents their objective as that's a bad typo, represents their objective as a linearly constrained quadratic programming problem, or LQP, which looks like this. Kind of a scary math equation, but what we see on the left is what we're used to for quadratic placers, which I talked about last month. We have the connectivity matrix, which says connections between movable blocks have these forces between them, and anything that has a connectivity, like for example, we have a matrix that's number of movable blocks times number of movable blocks. If movable block 2 is connected to movable block 1, then the matrix at 1, 2 would be a non-zero value. If they're disconnected, it would be a 0 value. So this is our connectivity matrix. This is our constant vector, which represents blocks connected to fixed points. And then over on the right is the new addition to this problem, which is a constraint matrix. So this is a constrained quadratic programming problem where we're solving for the wire length subject to the constraints that this block wants to be in this partition, this block wants to be in that partition. And I'll show how this is encoded. So this is our objective. And this can be transformed into an unconstrained form and then solved using conjugate gradient with a little bit of matrix math. They talk about this in the paper. I'm not showing this in this presentation.
Use like the Large multipliers and just add it to the objective? Or do they?
It's a little bit more complicated than that, actually. It's really cool. What they do is they actually do some like diagonalization and stuff like that, where they basically break it apart. And then they solve, instead of solving the original problem, they solve this problem instead, where they did a transformation.
Really fast.
Sure.
Okay, got it. So go to the top of the next one. Okay. Subspace. Okay. Okay, so keep going down. I can read this fairly fast. Okay, so I think they just take out, so they're putting the center of mass constraints, which means that they have fewer independent variables, which I think they've encoded in these new matrices.
Yes.
So that giving you a smaller matrix equation by essentially a transformation from the original variables to a smaller number of free variables. Okay.
Yep. And basically the short answer is you can solve this efficiently using a standard off-the-shelf conjugate gradient solver, for example, which solves this equation, or actually, sorry, it solves this equation for x star. And then you can use the inverse of z here to get, now obviously this is a lot of variables, so they also do some other tricks, but that's the idea. So we can solve this efficiently. What does that constraint matrix look like? Because that's kind of important to understanding this.
I guess the L is like step number.
That's a great question. I'm gonna get to the L in a second. I always give the L last, so because it stands for L. But that's going, I'm joking about that. But in the algorithm, this is actually the layer. So they make a partition, that's layer 1. They make 2 partitions in the subpartition, that's layer 2. And then so on and so forth. So it's basically the level you're at in the partitioner. Yeah. So this is how the constraint matrix is formulated. What we have here is, let's look at A, B, and C. These are the macros that we want to partition. And we say A, B, and C are going to be in this partition over here. And they use these little like L's to represent the row in the matrix we're caring about here. These are just integers. And what we can see here is A, B, and C are in this partition. So they're going to have some non-zero number in here. They didn't say what exactly this is, but this is probably some kind of weighting term or just some way of saying that they're in this partition. And all other rows are going to be 0. So that's how they set up the constraint matrix. And then similarly for D, E, and F, they're going to be non-zero for the partition that they're in, 0 everywhere else. This is how they encode their the partitions into the constraints. So if I can partition the blocks into their partitions and I give them their constraints, I can then solve my objective function, assuming that they're constrained to this region. And the idea is this. A may think it belongs over on this side over here, and that's where it minimizes the objective globally with no partitioning. Then you say, okay, A, assuming you have to be in this partition, what would be the best position now? And then it says, okay, well, originally I wanted to be up here, but if I had to be here, I might want to be a little bit lower. And that's kind of the idea here. By partitioning and then solving, we're allowing the blocks to say, okay, now that I know a partition exists, let me move myself so it makes more sense. Or that it optimizes myself a little bit better. That make sense?
I don't think they actually force the next, so are they adding 1 layer every time they?
I'll get to the algorithm and exactly when they do partitioning and
Okay.
when they decide to repartition to fix the problem of you can't just, if you decide too early on, you kind of ruin quality.
They go down multiple levels right away. They solve the solver, they invoke the solver, and then they go down multiple.
You are too excited. I'll just show you. I'll just show the example.
Yeah, no, go back. Forget it.
Yeah, I'm just trying to give like an overview of like how they formulated the equation. So how they do partitioning in the global placer is as follows. They call it cutting the Gordian knot. They actually did say this in the paper. So what they first do, and I'll go over each of these steps in detail. They sweep over different cut directions and values. So they'll sweep over all the different cuts they can physically make. And they find the one with the lowest cost, which is the cost of moving the blocks to the other partition if they chose that partition line, without making the partitions too imbalanced. So the idea is they don't want to move too many, they want to make a cut line that's like 90% of the chip and 10% of the chip. That's not very efficient. So they're trying to pick one, and I'll explain this in more details with a graph. Next, they use a min-cut approach to allow blocks to interchange between cut lines if they're near the cut line. And finally, they repartition after solving the global placement again at each level. So at each level, they do a partition, global placement, then a repartition using these new global place solutions. And they only do that once. They said that they tried it multiple times and they found that only doing it once made sense. It gave them the best trade-off. That's what they said in the paper. And I'll show this in the pseudocode. So that's how they do repartitioning. At each level, partition, global place, repartition, global place. Then they go to the next level, partition, global place, repartition. I don't know what the hell's going on over there. Okay. So partition, global place, repartition, global place, and then so on. And so that's how they're able to fix the problem of making decisions too early, or at least that's how they claim to have fixed that problem. So first of all, selecting the cut direction and the position. So they provide this graph in the paper. The idea is that this is me trying to cut at each point, basically. I'm going along the chip and just cutting at each one. Now, granted, this isn't physical position. This is how many blocks are on one side and how many blocks are on the other side. So this is 0 blocks on the left, all the blocks on the right. This is no blocks on the left, all the blocks on the right. Or, you know what I mean. So the idea is we want to find the point that minimizes this cost function, that cuts the fewest blocks. Well, I found it. It's right here, right at the bottom left. That's kind of trivial. The edges are very low in cost, but they're very imbalanced. And I want to make a cut that actually will balance things out the most so I can actually do a good partition here. What they say they do in the paper is they try to minimize the cost only within a small window region. That means between 0.5 plus or minus gamma, where gamma they said in the paper they found 0.3 to work well. So that means that they go between 0.2, which I did not do very well on the bottom here. Yeah, that's not correct at all. I guess I did 0.7 and 0.3. I think what I did wrong here is I did this and this, but in reality, it's the other way around. Whoops. Anyways, it's gamma. It's a variable. They can make it bigger or smaller. They chose 0.3. Don't worry about it. But anyways, if you look inside this windowed region, we find, there's a minimum right about here. So we're going to use this as our cut line. And what they do is they do this in both cut directions. So this might just be the horizontal direction. Then they do the vertical direction. And then they say, okay, which cut gave me the lowest cost? We'll pick that one. And so this is how they choose the cut direction and the cut position. Cool. That was step one. Step two is now that I've selected my cut, there are things that are going to be close to that edge which may want to negotiate onto which side they want to be on. So what they do is they allow interchanging between blocks via what they call the min-cut method. Now, the one thing I don't like about this paper is they said, we use the obvious min-cut method that everyone uses. They kind of didn't say it exactly like that, but that's how they kind of phrased it, and they don't describe it. So the paper didn't really describe it. I'm not as familiar with the min-cut method, but how I understand it is that blocks close to the partition line are going to interchange to decide which side they're going to be on by like kind of swapping which side they're on. So for example, they highlight in black here which blocks actually did the interchange. And we can see that this block may have been on the left originally, but then decided to move to the right afterwards because it was found to be slightly better. I believe the reason they do this is because they're sweeping from left to right, and then but then there might be many blocks on top of each other on the cut line, or maybe they're straddling the cut line in a weird way. This is to kind of like touch up a little bit and make sure the cut lines are good. Make sense? So that's the interchange of blocks. Finally, repartitioning. This is the thing that Vaughn was alluding to. If I just make a partition and then do global placement and that's it, you can never go back to the other side, you will definitely lose quality in that case because you're going to find out after solving that, oh no, something went really bad. This block was put on this side and I've solved it, and now it's like doesn't even know where it wants to go anymore. And I've actually made a worse solution. So what Gordian does is the following. Step one, very first step, we just entered Gordian. We globally optimize without any partition constraints. This is just basically straight up global placement, a quadratic global placement, no constraints. Step two, at each level L, so the level is the partition level, we're then going to partition the partitions at that level. Now, I know that's really bad terminology there. That's what that for each row in R is saying. Or I don't even know if that is row, but for each weird backwards P and R, what we're going to do is we're going to say, okay, for all the partitions that were created, so if I cut this in half, we're going to partition both of those halves. I've cut it in fourths, it's going to be each of the fourths and so on. So for partition each of the partitions at that level, following the previous two things I talked about, then we globally optimize with these new partition constraints. These get added together, basically. And then finally, we repartition once at this level and only this level. So we're going to repartition once, and then we're not going to repartition again for the same cut lines, I don't believe. So, and they show on the right how they do this. They say if overlap exists. Now, they define overlap within their paper as something like basically a model that, or a block that wants to be on the other side but isn't. That's what they call overlap. For each of the partitions, they're going to, in this level, they're going to merge the regions and then partition again. It basically means undo what I did last time, but using this new global placement information that I got from my previous global placement. We set up the constraints again, and we global optimize. And notice there's no for loop here. It just does this once. And then once you reach the end of this, we go to the next level, and then the next level, and the next level until we are sufficiently small enough. And then finally, at the very end, we finalize the placement. This is basically full legalization. We're basically just saying, okay, the global placement had a good idea. Now we're going to do the final little touch-up. I'm not going to talk about that in this presentation. Good? So yeah, what we see here about Gordian is they want to use bi-partitioning, and they did make this extremely clear in the paper. They don't use bi-partitioning to make the problem faster. You'll notice that for every global optimize they're doing, the global optimization is being performed over all blocks. And the partition, now the only thing you're only really making faster is that the actual partition itself is getting faster because you're reducing the problem size. But they make it clear they didn't want to use bi-partitioning for the performance implications. They say they want to do this because it's going to reduce the overlap. This is how they resolve their legality constraint. This is how they add the legality constraints into their solver. And what they do, in order to fix up the problem with bi-partitioning, which is early decisions causing problems, every single level gets repartitioned once to try and see if we can, okay, now that we know this is what's going to happen, let's try again and see if we can get a better partition this time. So that's Gordian. Gordian is the oldest one I have for using bi-partitioning. I'm sure there's other papers that do stuff like this, but this was the one that many papers in analytical placement cite. We're going to now move on to our next paper, which is going to be BonnPlace. So BonnTools comes out of Germany, and BonnPlace is a really fun paper because they really go into the nitty-gritty about the mathematics, which is why I really like their paper a lot. They also have some of the best visuals. However, their paper is very surface level. So the BonnPlace paper that I cite at the end of the slideshow is very short. Or sorry, it's not short. The BonnTools talks about every stage of the flow, from synthesis all the way down to routing. So they only have like 1 or 2 pages for each of the tools. So BonnPlace is described in only 2 pages. But in those 2 pages, they talk about a lot of really juicy stuff that I wanted to talk about. So this is how they're going to be doing it. What they do is they take their global placement, and much like Gordian, they're going to do what's called, they're going to do a partitioning. Now, in this case, they're going to do a multi-section. This is a generalization of bisection. So bi-partitioning is just bisection. You're breaking things in half. Multi-section, their work actually allows you to choose how many partitions you want to make. So they say they show 4 and 9 in their examples, but they said that you can get as big as you want. So it's kind of cool. But you can also turn it down and turn it into bisection. So that's why I include this in my bi-partitioners. The idea is much like Gordian. we select our partitions, and then we force blocks in that partition to go into that quadrant, and then we solve global placement again.
Question.
Yeah.
The thing is, Gordian doesn't actually force them to go back in the quadrant. They have a center of mass constraint.
Yes.
For that quadrant. Is that right? It does mean that some things can move outside the quadrant, which is why I think they do the repartition.
I believe so, but I'm not sure exactly.
But I'm pretty
that
sure
went a little over
they-
my head.
They have like, because it was a clever thing. They didn't like say your X and Y can't go outside your region. They said the center of mass of everything we put in this region must be in the middle of it.
Right.
And what that means is that some things could move outside the region when they resolve. It's just other people, like if you move to the right a lot, something else has to move to the left. And then the repartition can say, okay, now I'd like to actually re-encode my center of mass constraints. Maybe I made a mistake.
I see. I must have misunderstood it, but yeah, I think you're right.
I'm pretty sure that's what they do.
They do talk about center of mass when talking about the modules themselves, because how they represent the nets in the module is not actually as how we would like a clique or star model. What they actually do is they take all the modules that are connected over a net and actually find the center of mass of the entire net. And that's how they kind of talk about position and how they solve it in their equation. It went a little over my head, which is why I didn't want to talk about it too much in detail. I'm mainly looking at how they encode bipartitioning into their problem. And I don't want to just talk about that, but that's a really good point, Vaughn. I'll reread this and I'll correct myself next week if I find anything different.
I don't think it's very different from what you said. I think it's just like a part of what they're doing with these constraints. I don't think they're doing a min-max of like stay within your region. I think they're basically saying we decided you should be in this region, but that's encoded in their constraint matrix as your center of mass of these modules must be in the middle of that region.
I think that makes sense. And actually that would explain what you were talking about with how they actually formulate this, because you're right. You cannot just encode constraints without some kind of Lagrangian or some kind of trick like that.
But with that one, what you've done is you effectively removed some variables become dependent variables.
Right.
You can effectively re-encode some of your X positions as just the weighted sum of these other X positions.
Right.
So,
That makes sense to me. Thank you for that, actually. So Bond Tools takes a very similar approach. They perform multisection. Now that you know what region you're going to be in, you're going to solve for the objective. And I'm going to show how they encode this. It gets a little tricky, but I will talk about this. This one, I can certainly tell you they force it into their multi-section region. Because they make it very clear in how they do the formulation. But they have these really beautiful charts on how this works. So this is a multi-section that creates a 2x2. So you take your global placement, multisect it into a 2x2. And then for each of those, you multisect it into 2x2. And then for each of those, you multisect it by 2x2. And you keep going until it's small enough. And the benefit of this approach is, and I'll talk about the benefit in a second. This is just an overview. Let's look at their objective. Don't you just love nice, simple equations where they're not hiding all the complexity in one variable? So we have this nice weight matrix. So this is for all nets in your set of nets. The weight of the net, which can be any number you want. This could be like timing information, whatever you'd like. Divided by, and this is not, they don't use bound to bound. So they're using the regular old quadratic formulation for clique and star models, or whatever you want to choose. Divided by the number of pins in that net minus 1. Super nice. And then we have the sum of x PQ plus y PQ. There it is. So this isn't a very simple equation. They actually hide a lot of stuff within. In reality, these are honestly kind of simple, but it's read like tax law. So it's a little detailed. In a nutshell, here's what's going to happen. Let's imagine I have two blocks that are in the same partition. Then we're going to use this formulation. This is just the standard quadratic formulation. You take the derivative of this, we have a x minus x1, the x position of the one connection minus the x position of the other connection squared. Very simple. And then this xp and xq are the offset of the pins to the block. So for our case, we're going to ignore that for right now. But really all we care about is that it's the x position of the start connection minus the x position of the target connection squared. Cool. This is our spring force, kind of. Now, here's where things get a little funny. If P, the block that we're going to, the target, belongs to movable object C with offset this, and C is assigned to region R, I, J, and Q is fixed at a position with X coordinate U and whatever. What this is basically saying is we have a movable block C that's connected to something else that's outside of its region. We're going to set the position to be whatever the position of that bin is going to be. And then down here, we're going to do let me just double check my math here. See what offset this. C is assigned to region Rij. Q is fixed at a position. Oh, this is just the fixed block constraints. Sorry. I got mixed up with 2 and 3. Number 2 is just your fixed block constraints. What we're saying is that this V is a fixed point in space. We're connected to a fixed block. This is very similar to the quadratic formulations where we're just going to say position minus the fixed position squared. It's actually very similar to this one. But then down here, this is what happens when you have a movable block C connect to another movable block D, and they're in different regions. And all it really is saying is this. If P belongs to a movable block object C with offset this, what we're going to do is we're going to set it equal to, we're basically creating 2 connections here. One connects C to XI. XI, if I remember correctly, is... Which I don't know why it's not described in this figure. I apologize for that. It's basically the edge of your region, the edge closest to where this where D is located, and the xi hat minus 1 is going to be the other edge. So let me I can actually annotate on this, can I? Yeah. So let's imagine. Yeah, that's great. Let's imagine I had the following region constraints, or the following region where I had a partition, and I have one block that's over here. And if you recall from my presentation a month ago, we can linearly separate X and Y. So we're only going to look at the X dimension right now. This is a movable block M, or this is a movable block, and this is a movable block. What we're going to do, instead of connecting these 2 blocks together, I'm going to connect this block to this wall. And then I'm going to connect this block to this wall. Now they're not connected to each other, so they are completely independent. And what I've done here is actually made a fake fixed point on my region. What that means is that, and this is for all blocks. Let's say there's another movable block, these are connected. Another movable block, these are connected. And that's why this one's so complicated. It's actually the closest point inside of your region. So let's say you had a fixed block down here. This is going to connect like this and then stop here. What we're doing here is we're trying to keep M inside of this region. And if all of your fixed points are within a region, you could not possibly place this block. Its solid position cannot possibly be outside of the region. This is just kind of obvious. If you imagine these like springs, you'll never jump out. You're kind of stuck in the middle. So that's what's going on here. We have, this one is saying that blocks within the same region are connected like normal. When you're connected to a fixed block, you connect to the closest point within your region to that block. So let's say this one is fixed, then they're connected just like normal. And then finally, this one is saying, if you're in 2 different regions and you're both movable, connect me to the wall, basically. That's it. And then 0 if they're both fixed or we don't care about their connection at all. By doing this, what we have done is and now I need to clear this, so I apologize for that, but is this clear? As I said, this is a lot of stuff baked into these little equations, but the idea is I can take the derivative of these and then set up my matrix equations with my connectivity matrix and my constant vector. And in doing so, I now have a quadratic equation that I can solve for each of these partitions. And the benefit of this approach, I don't know how to clear the annotations. I think it's clear this. There we go. The benefit of this approach, so the benefit, this is a quadratic net model. The constraints are baked into the connectivity matrix and the constant vector. There's no constraint terms being added like what we were seeing in Gordian, which was causing us to make all those crazy matrix equations and center of mass stuff. This is literally baked in now. And each row and column in the partition can be solved in parallel. This is really important. Remember, we're not connecting movable blocks together. And because of that, everyone inside of the region are connected to each other and the walls. They're not connected to anything outside. So I can actually solve the global placement for both of these independently. And because of how conjugate gradient kind of works, it's not going to be linear with the size of the problem. So if I cut the problem in half, I can make things a lot faster. So that's what they're arguing for here. So by solving things in parallel and also by using a quadratic formulation, we can very quickly solve for these things. But there's a trade-off here. Because we're making these partitions and we're forcing things into that partition, I don't even think repartitioning is going to help us very much. So they have to spend more time thinking about how they're actually going to do partitioning. And how they do partitioning is very creative. But any questions on the objective function? This is how we bake constraints into the objective and make it so the conjugate gradient solver does the work for us. So how do we do multisection? We use the Hitchcock problem, the Hitchcock transportation problem. They show in their paper that they can actually solve this efficiently, but just how to read this. On the left, we have all of our movable objects. And on the right, we have all of our subregions that we want to create. And the edges connecting them are the cost of putting Ci into Rj. They do not explain how much about what this cost actually means, but the fact that they use Dij to represent their cost, I assume it's the distance that the object's going to have to move to get in there. That's my assumption here. And the idea is that we can actually, now, solving this as an integral problem, which says that C1 is going to go into R1, C2 is going to go into R1, C3 is going to go into R3, and so on. The actual integral problem is NP hard, but the fractional case can be solved efficiently, and they explain all the different algorithms they talk about in the paper. The fractional case says C1 is going to go into R1.2. C2 is going to go into R3.07. And that's what they say. And what they say here is that it can then be turned into the integral solution with very little loss in quality. That's what they say in the paper. And so that's how they actually do the multisection. And they have this very pretty figure to go with it, where they say, okay, this was my original global placement, forget the colors. And now I create this 3x3 region. And all the blocks that want to go into this top left region are going to be red. Everything wants to be in the top middle one is going to be yellow, maroon, and so on. And we can see how it forms the multisection. I'm not going to go into details on how they perform the multisection. They say it's formulated like a min-cost flow. That's how they say it is. And they say that there are a few other, they say that, actually, I'll just show what some of the wording they use, because I think it's actually kind of cool. And it's very short.
So if you put a source and a dest on that graph, you do flow, I mean, that'll solve an assignment problem.
Yep,
right?
That's exactly correct.
I'm not sure why they have to make it fractional.
They talk about it in this paper. They say if you don't make it fractional, it'll be very expensive. That's what they said. Let me see if I can find this. And can thus be solved in the standard minimum cost flow algorithms. Have super quadratic running times, and so what they do is they do some other stuff. And blah, blah, blah. And they show that you can actually solve this in a pretty efficient way in big O of nk squared, where k is the number of partitions that you're trying to create. So I think it's just one of those things where you just trust them that they have a good algorithm. But so that's how they actually do the multi-section. Once they have these multi-sections, what they're going to do is they're going to solve that global placement with the assignments, and then they're going to partition again. But I actually need to walk through this carefully. So we optimize a quadratic objective function with constraints baked into the objective. The constraints come from a multisection derived from an optimization problem to reduce the cost of moving blocks into each partition. They're very careful with that, using that really expensive, like this is quite an expensive algorithm to do multisection. Similar to Gordian, they do repartitioning after solving the global placement for the global partition. However, the paper does not describe it in detail. So I actually don't know much, if at all, about how they actually do this repartition. If I actually go into this algorithm, they only have one sentence on this, which says an important further step, because it's so important they describe it, is repartitioning, where 2x2 or even 3x3 subarray of regions are considered and all movable objects are reassigned to these regions. And that's it. Followed by multisection. So This is all I found in this paper. Now, granted, I don't think this is the only,
They're saying there, I think, is that, yeah, that they're, so chopped it up.
yep,
And then, as you said, their placement problem essentially becomes independent, I think.
Yep.
For each of the partitions.
yep,
They have sort of a step to go back up above that. So they take a 2x2 or 3x3 region and they essentially flatten it.
Yep.
That's what it sounds like. They
Yes.
Get rid of all the internal boundaries. They get rid of all, so they just say, okay, fine, now you're gonna solve for quadratic wire length in that, and then go back and multisect it again.
yes. I believe that's
So
what they're
they might
doing
go
as well.
back Up sometimes and say, okay, if they move around in this local region, now let's put all the cut lines back in.
Yep.
And now you're constrained to be in your sub-region again.
I agree. And I don't think it's a bad approach. I'm just mad because it only has one sentence. Now, I should be clear. I'm using the Bond Tools paper. There's another paper called BonnPlace, but the algorithm is very different than what's described here. So I think Bond Tools is an iterative tool where they've continuously built upon it and has many versions, but they don't have good version numbers. So Bond Tools, I like this one because it's the one that uses the multi-section and then updates the objective function.
Paper was more recent,
I think this one's more recent. I can double check that for you.
but you're probably, I think this is a tool flow that kind of evolved.
Let me just see. BonnPlace. Oh, I don't even have the paper. That's fine. But yeah, this is but I agree. I think it's just been built up over many years. So yeah, and the way they formulate the partition allows them to compute rows and columns in parallel. So what it allows them to do is actually get a lot of parallelism. And even if you don't parallelize it, because you're reducing the size of the problem, the conjugate gradient is actually solving a lot faster, or whatever solver you're going to use is actually going to solve a lot faster. So cutting this down actually does save a lot of runtime. You can tell from the paper they cared a lot about runtime because they even say specifically in the paper they don't do bound to bound. They don't do linear wire length. They purposefully chose to use quadratic wire length. And so I thought that was very interesting. But they do some net weighting terms. So that's all I want to talk about today. I actually thought I would only take 30 minutes. That took 45. So these are the references for the papers. So we have Gordian and then BonnPlace, but I'm really citing the Bond Tools paper. Next week, we'll talk about simple, heap, and G-place, which I think are actually going to be a lot easier to explain because we're not going to be fudging with objectives anymore. We're actually going to be using bipartitioning as a legalizer and then bringing that back into the objective through net weighting through anchor points. Yes. All three of these use fixed points. I couldn't actually find one like FastPlace that was a bipartitioner and used the movement. Like I actually tried to push the blocks like FastPlace did. I couldn't find any papers like that.
Did FastPlace not use, I can't remember all that. FastPlace not use anchor points or not?
They didn't use anchor points. They actually, like anchor points are applied and then you add a fake connection between them. It ends up being the same thing. What they do is they pretend like they're pushing it with a force and then they update the weight matrix as if it was pushing it. You'll find the math actually, I think, works out.
It's a little bit different, isn't it? Because you can do forces at infinity, which is a little different than putting an anchor point to the spring. Because as you approach the spring, your force gets weaker.
That's
Whereas
true.
a force that is just applied in the matrix equation never gets weaker.
I see your point, actually.
There's a paper called Kraftwerk that I think.
Kraftwerk 2, yeah.
Well, actually, I can't remember if that's the one that added forces. Anyway, sometimes people added forces. I've heard it's less stable.
I've also heard it's less stable as well.
Because of that behavior where.
You're right.
the
It'll keep
force
going.
never takes, right? Whereas a fixed point is like a spring. It'll get strong if you're far from it, but it'll get weak if you're close to it.
Ah, I see your point. You're right.
Force could just keep pushing you, like it's effectively right across the chip, right?
Yeah, that makes sense. Gotcha. That's all she wrote for today. Next week, I'll talk about these three papers, which I might as well just show my summary page because that might be helpful. So next week, we'll talk about simple, heap, and G-Place 3.0, who separate the legalizer using bipartition. They do legalization as bipartitioning, and then they feed it back in.